Welcome back to Indian Genes. We now continue our very interesting conversation with Dr. James Beacham and carry on where we left off in episode
1. If we were able to measure it in more than 3 dimensions of space, so you and I only exist in 3 dimensions of space, but maybe the extra gravity that we're missing is leaking into spatial dimensions that are invisible to you and I. Could be something that's so small and curled up, and it's at every point in space all the time. You imagine like a tightrope walker, right? If he takes a rope and puts it across 2 buildings with a street underneath, right? And as the tightrope walker, from a distance, you see her walking across the street, and she only has one direction to go in, one dimension, right? Forward or backward. And she can't go side to side, otherwise she'll fall. So she has one dimension. However, then if you zoom in to the rope itself, and what if you're an ant, a tiny ant on the rope? The ant, in fact, has one extra dimension. He can go forward and backward, but he can also go around the rope. So there's this extra dimension of space that was invisible to you looking from a far distance. So maybe every single point in space, there's an extra loop, spatial dimension, and maybe that's where the extra gravity is leaking into. And possibly we could find an evidence of this by creating one of these little kind of like, hyperdimensional graviton things, or one of these mini black holes that would allow us to test this hypothesis. We don't see any evidence of this so far, but we're still looking for these type of things.
I think that that actually describes the initial requirements for the string theory and Kaluza-Klein when they spoke about 11 dimensions for gravity to be taken into account. But I think before we get there, I just want to come back to, like you spoke about special relativity, Einstein actually brought gravity into the picture. I think Schrödinger, when he spoke about the particle and duality, particle and wave functions, that was a very interesting part of us coming to understand quantum physics, so what made it so interesting as well, right?
Yeah, so the notion of the wave-particle duality is a particularly important version of, I think it was Feynman who once said that any physicist worth her salt has about 6 different ways to describe the exact same phenomenon, right?
He also said if anybody understands string theory, or he says nobody understands string theory.
Yeah, he said nobody understands string theory, but then I don't remember if it was Feynman or somebody else, but another one of the famous quotes about quantum mechanics, right, is that something about how anybody that says that they understand quantum mechanics hasn't thought about it for long enough.
But it brings in the probabilities into our lives if it's at the microscopic level. But then that also does mean, right, it brings in the thought of the whether it's free will versus a deterministic universe, because at some level, if you have a choice, or if every electron has a choice till it actually decides or till somebody observes it, does that not fit in with everyone making a decision and then that decision becoming realistically manifesting in the world?
Yeah, I mean that's a deep question, right? I mean, what do you think? Do you think that our universe can be successfully thought of as, do we have free will in this case?
I think when it comes down to free will, I think we do, but I would say limited free will. And when I say limited free will, I mean that there are options for everybody. But I still would have to connect it to the multiverse, because whichever decision you make, you're going to keep branching out. And once you branch out into another universe, the previous one that you left, you're still going to be left with choices there. So it's like taking one choice and moving on, but that doesn't mean that the other 99, for example, are not there anymore. It's still there. And so I think in every level, people have moved on with a choice that they've made. I don't know if I'm making sense to you.
Yeah, I mean, I think it's a good sort of analogy for the way that humans operate, for sure. I mean, at the end of the day, it's one of these things that's it's open to interpretation, and it's kind of more or less unverifiable, right? I mean, we can have these conversations, but there's really no experiment for me to that I can design right now to determine whether or not humans themselves have free will.
What do you think? From what you have access to much more data than most of us, and from what all you can see going on around you, what is your take on free will?
I think that humans definitely do have free will, but it has to do with it's a matter of scale to me. It's a matter of how different concepts are valid in certain regimes and they're not valid in other regimes. And we know this is the case in physics, right? I mean, if I, for example, me walking around the world right now, just through physical space, I don't actually have to care about quantum mechanics at all. It doesn't matter if quantum mechanics is real or not. It really doesn't. To me, walking around, in an agrarian society, way before anybody had telescopes or electromagnets or anything, I could, I could get, some livestock, and I could, I could let them graze on the land, and I could marvel at the beauty of nature and of mountains, and I could just exist right there. I never would have to care about whether quantum mechanics exists. And so in that case, in that sense, these are the things that are valid to us. In humans organizing themselves in society, those things are really valid, right? It actually does matter how I treat, my other human beings. It matters whether I'm kind or I'm evil or I'm, mean or I'm charitable. These sorts of things, I do have a choice to make these happen. And whether or not I'm able to point toward, the fact that deep down inside, deep down at every single one of our particle levels, there is some kind of constant, unceasing level of, quantum determinism going on and branching off into multiple universes or whatever you want to call it. That's totally irrelevant to me. So, the reason why I always get a little bit skeptical when people start talking about, quantum mechanics and free will is that I often think that I always have to wonder is like, why are they bothering to have this conversation? Are they trying to find some source for some of their bad things that they've done in their life? It's like, oh well, quantum mechanics made me do it. It's like, oh well, I didn't really have a choice because this is the type of universe that that I happen to find myself into, and this kind of this led me to do what I'm going to what I was doing. Right. I mean, for me it's less interesting than how we as humans can take these lessons, take these understandings of nature at the smallest possible scales, and use these to construct a better world. I use this as I like to think of quantum mechanics as being I like to point it out. It's like one of the things that a lot of people are thinking right now is the future of computing, right? If we were once we get to quantum computers, right, will we be able to more or less simulate things at such high scales as and eventually once quantum computers get better and better, and we can scale them up, could we in principle, for example, simulate the human brain, and if we can simulate the human brain, could we simulate human consciousness, which I think is very ill-defined. In that case, could we then find the source of how humans make their choices, and could we predict the way that humans are going to act with complete accuracy? And I think that at the end of the day, we probably cannot, right? I mean, even though, because again, down at the moment of individual, particles constantly making these constantly branching off into different realized universes, realized realities. That's still going to be basically, we can calculate one particular version of reality, ours, but in our reality, in our universe here, if we're able to accurately do some kind of large, sample of like a large ensemble of similar experiments for similar universes where all of the different possible quantum choices were made, I think that is more or less going to be outside of the realm of computation,
right?
Ever.
And you did speak about, you touched on consciousness there. I think that is such a big topic. And I'm looking at the upcoming podcast on consciousness itself. But also, like you mentioned, James, I mean, I probably look at it, if you're looking at time, you spoke about the universe being 14.4 billion?
13.8.
13.8, okay. And I'm trying to put that into a common man's perspective. Between time at that scale, I can't even comprehend. So I'm thinking about this. If I'm sitting at home, and I'm sitting at home from, let's say, 12 o'clock in the afternoon to 12 o'clock the next day, and the doorbell rings once, that's how long we've been around.
Ooh, probably, yes. I think that would make sense, right? I mean, I haven't done that calculation, but you could do the calculation. You're absolutely right. Yeah. I mean, that is totally humbling. Exactly what you're getting at, right? The fact that humanity has been around for such a small slice. Yeah.
So why should we even think we are at a stage now that we are on the brink of let's say, forget understanding consciousness or creating another human? So I don't know. I just think that, it's a flicker, or I think where we are at the moment, we need to enjoy. What we are doing, we need to enjoy. because this is the only reality, and we need to look after each other more than, like I said, it's just a doorbell.
Yeah. No, I think you're absolutely right. It's one of the most important lessons for me as well. There's so many things that give you this sense of give you this sense of wonder and awe and humility and when you study physics, because it allows you to see all of our human problems and our fightings and things like this in such a completely different scale, right? It's like we have been around for such a small amount of time compared to the size of the age of the universe itself. It's like, depending upon your perspective, the universe doesn't even know that we're here, right? I mean, why should we think that the things that cause me so much problems and the source of us fighting amongst ourselves, these should be completely, these should be so smaller than, these should be so much less important than the fact that we have this tiny slice of existence, and we really should take the full advantage of it to try to construct a better world for everybody. It's just a shame when you see terrible things happening, because people get so wrapped up in the sense that that's like their entire life. That's the most important thing, when we really have this tiny slice that we should work together on, on.
And you break that down to the average individual lifespan. That's you don't even hear the doorbell.
Yeah, the humbling experience of being a human alive, to even ask these questions, right? It's just so absurd in a way and so wonderful at the same time. It just gives me a very humble perspective. I mean, in fact, there's a talk that I like to give that I've given a few times. Maybe, some of your listeners might enjoy it. It's called "What's Outside the Universe," and there's a good version of it online that's from Amsterdam. Pretty good production values on that video. Okay. But it really kind of goes into this. It kind of dives into what happened at the Big Bang and why the particular way that the universe expanded at the moment of the Big Bang, and as we know, it's actually had 3 different epochs of expansion through its history. For some reason, 3 billion years ago, for some reason, the constant the kind of linear expansion that was going on started to accelerate and increase. So this is this notion of dark energy that's been something that's driving the expansion of the universe right now, that we don't really know what the source of it is, but it sort of turned on a few billion years ago. Anyway, there's so many of these things that lead us to the conclusion that in fact we might not be the only universe, and that's even more humbling, right? You think about the fact that not only are humans just this tiny, we have existed for this tiny fraction of time, like you said, an individual doorbell ring for an entire day. We have existed for this tiny fraction of time compared to the entire history of the universe. And in fact, we might not be the only universe. There could be other universes out there. We have no reason to think that any of them would have life like ours. Maybe they would, due to statistics. Maybe there's inevitably going to be some other universe that's just like ours, except somebody listening to this wore a different color of shoes today, that kind of a thing. And so there's this sense of like awe and wonder and also humility, the fact that we exist like this, and it really gets at the heart of what are humans really? What are we as not just as a species, because we know who we are as a species. We're primates. We're related to other primates and other species so closely, and not just biological life, because we know how that evolved. More or less starting from very tiny single-celled organisms, and eventually, after a very long amount of time, you get to us. But why do humans need to exist in a universe like ours? Why is it inevitable? Is it inevitable that humans like us, something like us, would exist? And are there, why is it necessary for some kind of set of beings like us that have something that we can define as sentience and consciousness? Why do those things have to exist? Is it inevitable that we would exist? And of course, as you know, sometimes some thinkers throughout history have thought about this notion that maybe we humans are really the things that the universe grew to start to ask questions about itself.
The anthropic principle?
It's sort of like that, but you can think about the anthropic principle, meaning that it's sort of just because we're here to ask this question, to ask these kinds of questions about science. Yeah, exactly. That somehow things had to have been arranged in a particular way for us to evolve and to ask these questions. And one way to answer that, of course, is that Okay, maybe, because it does. It goes back to something that we didn't get a chance to touch upon, but there's so many things in nature that we observe that we don't really have explanations for, like why they are what they are. And as physicists, that's very dissatisfying, right? Mm-hmm. If I see some kind of physical phenomena, I want to have some kind of mechanism or some kind of description so that I understand why and how that exists. And for certain values of things that we measure in nature, there is no reason why they are. Like the electron charge, why is that the number that it is? There's no reason. Why is the gravitational constant that value that it is? There's no a priori reason for that to be the way it is. The Higgs Boson mass, why is it the value that it is? It doesn't have to be that. It is what it is. Yeah, pi, exactly. These things are just numbers put there by nature, and we don't control them. We can only measure them. And if some of these numbers were very different, or even slightly different than what they are, we'd have a very different universe that we'd exist in. So one of the ways that you could come up, one of the ways that you could, you can try to explain this is that maybe these values are really just values that are taken from some kind of statistical distribution, right? Because as we know, nature loves statistical distributions. And so maybe the value of, our gravitational constant is just one of an almost infinite number, or an infinite number of gravitational constants, each one of which of those is actually realized in a different universe that also was popped into existence at the moment, right before the moment of the Big Bang, when the fabric of space started to inflate. And because this inflation, in fact, should go on forever, and it popped up our little bubble of space, which then, it was inflating exponentially, but then it slowed down. And so our universe is a kind of a little bubble that popped up when the fabric of space started to expand. But if that's true, then there could be an almost infinite number of other bubbles that popped into existence. So each one of these universes could, in principle, have totally different values of the same kinds of constants that we see here. But those values would be totally different, and most of those other universes would be completely empty voids and very boring, and you never be able to even host a podcast in them because there's no one around to listen to it. So that then you get to that conclusion. It's like, so our universe exists because everything was just the right, because one universe had to exist, at least one universe had to exist where all the constants were just right to allow these things to exist and for humans to evolve and for us to be able to ask these questions right now. And in a way, it's just, the most profound thing to me is really this notion that I think it was in fact Wheeler, the physicist Wheeler, who had this wonderful diagram in one of his books that was the English letter U, right, for universe, and at the top left part of it, the stroke of the letter is actually quite narrow, and then it gets wider as it goes down to the bottom, and it goes to the other part up to the top right, and it's much wider, and then there's an eyeball at the edge, and the eyeball is looking back at the initial part of the U. So it's almost as though humans were the thing that the universe evolved to start to ask questions about itself, and that's a very kind of profound thought to me. That image has more or less haunted me my whole life.
Yeah, and you spoke about this fine tuning. It's very interesting that it still is very interesting that if the multiverse is true, then the fine tuning doesn't matter. It's irrelevant because, like you said. But if we are talking just from where we are at the moment and what we can observe, and there have been new theories where people are talking about are we a simulation, are we a computer simulation, and that got me thinking, if we ever were a simulation, I'm just trying to understand, for a person in a simulation, how far could that person search, or how much could that person know about a computer program? So if you had a computer game, there were limitations to how much the person within that game could explore. It would be very difficult for that person to first of all then get to have a view from the outside, or even the intent. So if that did happen, what are your thoughts on what's been going around about, are we living in a simulated universe? There are a lot of very serious scientists today talking about it, saying, yes, we could be.
Yeah, I think it's a fascinating concept, but I continually go back. I always go back to the notion that how can we design an experiment to verify this, right? And that's the part, as an experimentalist, I always have to go back to that, right? Because, ideas are ideas are ideas, and I love ideas, but until we can come up with some kind of experiment to, in principle, test this idea, it just remains just a good idea.
Or you wait for a reboot to happen and see the buzz.
Exactly. Exactly. Yeah. And so I think it's entirely fascinating, and I love to think about these things too, right? I mean, if, as you pointed out, if you were to imagine yourself existing in like a video game or like a simulation, how would, and this idea came to you, it's like, oh, I am living in a simulation, possibly I'm living in a simulation. How could I ever, come up with a way to get outside of that? How could I ever have a perspective that is, that expands beyond what my existing parameters are, my physical parameters. In a sense, you can't, right? Even though you can conceptualize the idea, if you can't ever, because the idea itself has been formed within this framework, there's literally no way for you to escape that framework. You can imagine something beyond that framework, but the framework itself still defines all of existence. How are you going to get beyond that? In a sense, that's related to this notion of, are there multiple universes? Right now, I don't even know what it means to define the concept of exchanging information with another universe, because all I have is this universe. This is every word that all of my experiments, all of my thoughts, all of my ideas are defined within this universe itself. How could I ever possibly come up with the concept of exchanging information with another universe? And in that sense, how could I ever possibly come up with a way to escape a simulation? Escaping the simulation, the concept of escaping the simulation is still defined within the simulation itself.
Right. Then for you with entropy, then you would agree with more than a simulation. What about Boltzmann's brain?
I don't know. What do you think?
I think that's a very interesting one, because when Boltzmann spoke about entropy, and when he was talking about the possibility of the whole universe aligning itself with an end in mind, it was probably easier for a brain to exist in the universe with all the memories of being a human and memories of life, and rather than a whole human body going through evolution, the creation of the earth, animals, and then we come up with the brain. I think a good analogy for that was the universe would probably give you the chances of, if you wait long enough, you would get a steak from a universe rather than you having to go through everything else to the time we invented a grill. So that is also another interesting factor, right? Because I don't know whether all of this is being done with an end in mind. It could just be a consequence. It could just be an accident. I don't want to think about what it is, but I think we got to think of all.
We absolutely do, and I totally agree that the concept of the Boltzmann brain is this has to come up anytime you have a discussion of this, right? Because when you apply this to ideas of the multiverse, right? Again, anytime you talk about this type of thing, though, is that to do these calculations, to even try to put a number on the probability of human life existing in a universe like ours, or the probability of maybe other intelligences in the universe, or the probability of other universes existing parallel to ours, either from inflation or from like quantum mechanics, many worlds hypotheses, or things like this. All of these probabilities are very ill-defined to me, because to make that calculation, you have to make a lot of assumptions behind the scenes too. So even Boltzmann, the concept that it's somehow like it's often described as sort of like it's more probable for a single brain to like spontaneously come into existence in a void, right? Than it is for our universe to have come around the way that it did. Why is that? Why? The thing that I stick at is the first words. It's more probable. Why is it more probable? To put any behind the scenes, you have to make a bunch of assumptions about probability that go into that I don't think are so valid in this case. We have one universe for us to look at, and it doesn't necessarily mean for me it's not such a fertile direction for experimental research to make kind of hypotheses, or to talk about concepts like this, because again, at the end of the day, we as humans do exist, and we kind of know how we have evolved. In the future, there's probably as we know now, given the fact that we know a lot now about the expansion of the universe and in the future of the universe, and what the universe will probably do. It will continue to expand forever and ever and ever. At some point, you can imagine that since there's basically an infinite amount of time in front of us, there will probably be more beings like us that will come into existence, or maybe even more advanced beings than us at some point. So why would we think that we're so special, or why would we think that we're not so special? Again, I don't really trust the calculations with respect to probability that go into this. I'm not so much of a Bayesian, let's put it that way.
Okay. And even when it comes down to one particular fact that I just want to come back to, where we were talking earlier about the probability and the wave and the duality function. That in itself seems to be a sticky point, right? Because if we cannot break this down, or if we cannot get to a fact that where we are talking about probability and every electron or every possibility at the quantum level has to be observed, you're putting the human agency into the universe. Because if I don't observe it, it doesn't happen. So that to me is a little bit striking, because I get everything else. I understand the fact of there being a difference between the quantum world and the Newtonian world. But why does human agency and my observation of a particular system have to have an impact on it? I mean, so what happened before the doorbell? What happened when humans were not around? Was there nothing around?
Yeah, I don't have a very good answer to that. I mean, it's an open question, right? It's this notion of the observer paradox, or in quantum mechanics, it's very clear, right? I mean, there's certain things that can exist in a multiple different concrete states in some kind of superposition of them, right? It's not as though it's existing in multiple distinct states. It's that superposition is a different concept, right? So we have you have possible outcomes, and they are mixed together in this superposition of possible outcomes until you make an observation, which then collapses into one of them, right? And the way that collapse happens, of course, is the source of a lot of kind of hand-wringing about the consistency of quantum mechanics and all that kind of a thing, and whether it's a valid description or is it just something that our human brains did not evolve to really understand at an intuitive level. And in that sense, the concept of superposition is fairly straightforward. It's anybody that tells you the quantum mechanics is not understandable, it's like, I mean, it is understandable. It's just that it's not so intuitive to us. It's not, intuition is based upon experience, right? And experience is, for us humans, is totally just, the small amount of time that we've existed and we've evolved in this very, very fuzzy, very, friendly set of conditions, to exist in the universe. And so coming down to that, it's like, I don't necessarily know if choice comes into it at all, because for me, you do have a wave function, you do have superposition of possibilities, and then once you make an observation, it does collapse. The particular wave function has the possible superposition of states, does choose one of them, and it chooses the one that you've observed. But could there have been other possibilities? Absolutely, yeah.
And you spoke earlier about consciousness as well, so I want to ask you a question. What about the possibility of consciousness? Like you said, we have four forces in nature. There could be another force. Yes, there could definitely be. I think vibration could be another one. But if you think about consciousness, what is the possibility of somewhere in the future us figuring out that, like the Higgs field, consciousness is a field as well that permeates right through the whole universe, and it just like the Higgs particle picks up matter or accumulates matter. Consciousness could be that matter then maybe interacts at some level to give you different levels of consciousness.
I intimated this earlier, but for me, the concept of consciousness is so ill-defined, even amongst professionals, that I have a hard time digging into it in a lot of the directions that some people want to go when they want to connect it to physics, right? Because physics does very particular things, right? It's a very particular field that is trying to come up with mechanisms, trying to come up with mathematical descriptions, and then mechanisms by which certain physical phenomena occur. Right? Consciousness, as it seems, is clearly something that is happening at the biological level. Obviously, it has a physical component to it, right? Because what is if you ask, because what I'm getting at is I want to define consciousness first. I want to understand what we mean by that before then I can ever assent or think about this concept of like a consciousness field, because at first glance that makes no sense. There's no way to come up with the notion of a consciousness field in the same sense of physics sense as any other fields that we know of, that I could define, that I could give some kind of operators to. I could describe with a Hamiltonian or Lagrangian or something like that. I don't know what it means to do that until we define what we mean by consciousness. So if I were to define what consciousness is right now, to me, clearly, it is a set of neurological impulses in the brain. It's the way that these things come together. Is it very, very complex? Yes. But it doesn't mean that things that are, just because something is horribly complex, doesn't mean that it's still not explicable with existing physical phenomena. So this concept of consciousness is something that I think, to me, it's difficult for me to dive into it, because it's not so well defined from like a physicist perspective. I totally understand that the physicist perspective is sometimes a little bit hardcore and extreme compared to what scientists want. But it's, again, for me, it's just so difficult to dive in, because I don't really fully understand what people are getting at when they are trying to understand this in a deeper way. And
I was just referring to panpsychism there, but I agree 100% with you. I'm totally a believer that that consciousness does emit in the brain. And for me, one very clear example is the use of psychedelics. If psychedelics have an impact on your behavior or have an impact on your thought processes, then I think it's very clear that the psychedelics do affect some part of your brain, and we are studying that now, and we are being able to localize what particular chemical affects which part of the brain. So I think that is pretty clear. Once you know that you can touch certain parts of the brain and have certain results or have certain reactions, then I think that there's no more need for something outside that.
Right. Right, and you're right, and of course, all of that being said, right? I mean, I'm being the hardcore physicist skeptic just because that's the way physicists are, right? And we're horribly skeptical. I mean, we could do an entire episode about the uses of artificial intelligence and particle physics and physics itself, right? It's like, for example, in physics, in my field, in experimental particle physics, we don't use a lot of AI methods. Primarily, because, well, for one reason, we don't really need them so much, because our data is very highly structured. It's a very large, data set. It's arguably the largest unique data set in human history, but it's very structured. And so the hottest and latest in deep learning is not so applicable to what we do. We do use it because we're interested. A lot of us are just we're still sort of, coding nerds also, so we really want to. But really, we also don't like a lot of artificial intelligence ideas, because they're black boxes, right? And there's no mechanism by which I can, if I were to dump all of my data into some kind of perfect deep learning algorithm, and it spat out a bunch of discoveries, new particles that I had missed, then I would want to know. I wouldn't trust those, because I would want to know how they got to that. How did it go from the raw data into the discovery that it did? And very, very often with deep learning algorithms, there's not they're designed to take advantage of these correlations and find things that were not so visible before. So it's more or less of a black box in that sense. It's also when we start talking about things that have not so well-defined physical attributes, the physicist, the kind of highly skeptical physicist comes, switches on, and I start to, trying to understand a bit more about what is the words that we're trying to use. But, to me, it's also, there's also a kind of a, there is a very interesting part of it as well that, to me, does come back to physics, is that I don't know if I could ever describe in a physical sense some kind of consciousness field, but there's no reason for us to think that there would not be other types of sentient beings that would have a different type of, for lack of a better word, intelligence than ours. Our level, if you want to have some, it seems a good heuristic or a good conclusion to come to the conclusion that at least on Earth, in terms of biological life, beings that exist, there are definitely different levels of intelligence or consciousness or sentience that that we can identify, right? And for us as humans, right? If I take the Newton's Principia, and I give a perfect copy of it, to a bonobo, the bonobo is not suddenly going to understand, Newton's theories, right? Because the bonobo interacts with the world in a different way than what we do. And so, why would we assume that we are the highest possible version of intelligence that a universe like ours could evolve? It's entirely possible that there are other types of intelligences that are way higher to us, and maybe they're giving us the answers all the time, and we don't have the intelligence capacity, like in a literal sense, to understand it, or to even really to understand it. The concept of understanding to us is defined within a very certain set of parameters. There's no reason to think that we should be the highest possible thing, and it's entirely it's totally hubristic to think that we would be. Why would the universe only evolve us? Why would we be so special? I don't think we're so special.
And you've brought in an important, a very interesting fact, because then it comes down to scientific truth or the ultimate truth, because we would never know till we do not know what happens in the end, because like Nietzsche says, if it doesn't kill you, it only makes you stronger. So I think we would never know that answer. I mean, we do know it in the short term, but in the long term, that is still an open question.
Yeah, very much so. And it's an open and fascinating question too, because again, even though I'm being the hardcore, skeptical physicist, which I always will be, I also have the part of me which is the one that constantly wonders about those things and has a very kind of almost poetic, wonder about this. It's like us being the only possible, planet in the universe that has beings like us that interact with the world like us. Okay, maybe again, I don't want to put the word probable on it, but it's entirely possible there are others. It's just that they're separated by either space or time distance that we haven't had a chance to interact with them yet. From a purely physical perspective, as far as we know, as you know, the size of the universe is an interesting idea right now. We know that the overall size of the universe is very, very large, and in fact, it's much larger than our observable universe, right? And our observable universe is a volume of space defined by all of the stuff that could ever possibly send us a light signal that could get to us that we could verify it exists. But that can't be the entire universe. There has to be more stuff outside of the observable universe than what we will ever. And if it's outside of our observable universe, by definition, we'll never be able to observe it. We'll never be able to verify that anything there exists or exchange information with it. Maybe just so you start thinking, okay, where do I place the scale? Where do I place the parameters or the volume of range by which I am able to say it's probable, quote unquote, that at least one set of humans like us evolved in this, within this volume to then get to this point to start asking questions about the universe as curious beings. And do I put it around our observable universe? Do I think there's more inside of our observable universe, or do I say that there's a minimum of one in each observable universe after 13.8 billion years on average? And so in these other observable universes, maybe there's at least one there as well. Maybe there's zero in one of them, there's two in another one. Again, I have no idea how to put these probabilities together. I'm not really one of these people that puts so much credibility in these things like the Drake equation and things like that, because there's so many assumptions that go into that are sort of just like picked out of thin air. You have to make choices about them, and they're still totally human choices.
Yeah, and you were also mentioning about how far we can go with as far as space technology is concerned, or when we talk about consciousness with AI or human beings, and I have my doubts, not my doubts, but I would just wonder. If can you tag an electron? I don't think you can, right? All the electrons all over.
No, you cannot tag an electron.
Yeah. So if you can't really do that, then how would machine learning work?
When we say an electron, right? I mean, what an electron is an individual. Kind of goes back to the thing we were talking about earlier. One of the things that connects all of us as humans, and that if we think about it in a metaphorical way, it should really make us feel like we're part of the same continuum rather than individual beings that are kind of fighting against each other or kind of, fighting over resources or something. In fact, if you look at us closely enough, we are these tiny particles, but these particles are really just temporary vibrations in some kind of quantum field, because the more accurate description of the entirety of the universe is not individual chunks of stuff like electrons or protons floating through a space, but instead the fundamental objects of the universe are in fact these quantum fields. And so, the Higgs field is just one example of a field, but in terms of quantum particles, quantum fields are the things that are the fundamental objects, and then an electron is a temporary vibration in this quantum field. And it vibrates into existence, and sometimes it's stable for a very long time, but then maybe it gets absorbed by something else, So as humans, that's really what we are. We are gloriously temporary vibrations in quantum fields in a particular stable configuration, and then eventually we will, be subsumed back into the continuum just like everybody else. So in a sense, this connects all of us in a very, very fundamental way. So an individual electron, as a chunk of something, you can't tag it, in the sense that I can't put a tag on it before a collision. So for example, if I take an electron-positron, they collide and make a Z-boson, and then the Z-boson lives for 10 to the minus 15 seconds, 10 to the minus 23 seconds, something like that. And then it decays into another electron and a positron. That electron that comes out the other side is not, quote unquote, the same as the one that went in. Okay. There's no way for me to tag an electron in that sense. But what I can do is that, because again, the thing to remember for me is that physics at its smallest possible scales doesn't so much care about the names of things, and that's both a physical statement and also a metaphorical statement, right? The universe doesn't care that really that I exist with the name James in this combination of vibrations and quantum fields, right? But it also it means a very physical statement. So because the rules of quantum mechanics are very different from the ones of ours. As you know. Particle collisions are not like car collisions, right? They have totally different rules. In a car collision, we care about, the names of the people. It's like, oh no, is John okay? Is Mary okay? These things, and we care about where the tire is, that kind of a thing, is that maybe the tire fell off of the car. But for particle collisions, they don't care about that at all. The thing that particles care about, the universe really cares about is conserved quantities, the conservation of energy, conservation of momentum, conservation of charge and spin. As long as these things that we observe are conserved quantities, as long as those are conserved before, during, and after some kind of event, you can do whatever you want to inside there. So, for example, this is how a Higgs boson is in fact created. When two particles collide, two protons, two of the quarks maybe get pulled out of these protons. Those two quarks hit each other and they annihilate and they cease to exist. But their properties are reconstituted into some new thing called the Higgs boson. And all the same properties of the quarks are still there. They've just been rearranged into a different form. Then the Higgs boson lives for 10 to the minus 22 seconds, and then it splits into, say, a muon and an anti-muon that hit our detector. The muons are totally different particles than the quarks that went in, but because all the properties are still there, all the charge and the spin and the different types of isospin and the energy and momenta, those are all still conserved. It's totally possible for that to happen because the universe likes to reconstitute things. So in that case, an electron is just a little vibrating quantum packet of a vibration in a quantum field that has certain properties, physical properties that are conserved. So all that being said, the rules of quantum mechanics, the rules of quantum field theory, how these electron-positron come together and annihilate and maybe create a Z-boson, something, all those rules, they are deterministic. I mean, quantum field theory is a deterministic theory, right? It's a deterministic framework. Therefore, you should be able to teach a computer how to do that, and we can. So that's how, at the particle level, in fact, we collide these protons at high energies, and then, something happens and a bunch of particles fly out, and then they hit our detector, and that detector, the raw data, is just a bunch of blips. It's a ones and zeros as to, you have a geometry that's defined by this three-dimensional object, and then you have a bunch of different possible places that could be lit up by a particle passing through them, and then it's either, lit up or not lit up. And so in a sense, you can think of it as, a bunch of ones and zeros. And so once you have all that data, you can then we then run algorithms on it to reconstruct this raw data into objects that human physicists can analyze. So if I see a bunch of blips coming out from the center of the collision, and they all go in one kind of nice curvy direction to make an individual track, and then there's a blob of energy that hits this thing called a calorimeter right behind it, and then I can reasonably conclude that is an electron, right? So it's an object, it's like a particle like an electron that hits our detector that we can see. So again, all of the rules of the quantum mechanics down at the moment where the collision happens and then things start to fly out, that's deterministic. In fact, we can take the raw data and we can we can actually code up the same rules of quantum field theory in our simulation and then create simulated data, and we can compare those two things. In fact, that's a large amount of what we do. We do simulations of what we would expect, if a new particle existed, like a quantum black hole or an exotic cousin of the Higgs boson, or a dark matter particle, a dark photon, and then we compare that to our real data to see whether there's evidence of a new particle or not evidence of a new particle. And so, in that sense, we can simulate nature. We can simulate nature at its smallest possible scales, because quantum mechanics, quantum field theory, is a deterministic theory. So there's also, of course, the limitations to our calculations, because within the physics itself, within the model, there's lots and lots of subtleties, and there's lots and lots of degrees of precision to which you can go that are almost infinite in nature, right? So we have a certain amount of accuracy and precision we can do now with our current computing resources. In the future, with quantum computers, maybe this will get better and better and better. So because our computing capacity will get better and better and better, so our ability to predict what happens from a quantum field theoretical perspective will get better and better. So in that sense, you scale that up, and at some point you could, in principle, simulate an entire human brain, and then maybe simulate an entire species.
Wow. But I think the limitation there for you would not only be the limitation is going to be like we started, is going to be the energy. And so to actually get the extra energy needed, or to find out, you said you were talking about different levels of particles and the energy that was needed. So you'd have to build a bigger collider. Yes, very true. We will. I mean, there's this limitation. In particle physics, there's in my field, we call it high energy particle physics. There's two, and just in general, collider physics, right, where we're smashing things together to try to see if nature can create something new, some new particle that that it does not exist in abundance around us right now, maybe only in existence back at the moment of the Big Bang, 13.8 billion years ago, but we can recreate it in the laboratory. The whole name of the game is that there's two ways that you can miss new discoveries, or put another way, there's two ways that you can make new discoveries. One is in terms of energy, right? So this is this notion of going to bigger machines, bigger tunnels, to allow the particles to get to higher and higher energies, and through E equals mc squared, maybe if nature has this particle with a high mass m, it's entirely possible. But we'll never know about it unless we build a bigger collider to get to higher and higher E's. And this goes higher and higher and higher. The other way that you can miss a discovery is at our existing machine, for example, the Large Hadron Collider. You might wonder, it's like, okay, we've been running this thing for 10 years, and we have a lot of data, so it's at this fixed sort of high energy. We've been running this high energy for quite a long time now. So far we haven't seen any big discoveries beyond the Higgs boson, so why don't we just turn it off? We already looked, quote unquote, at this high energy. It's because what we're looking for is extremely rare too, right? I mean, if we do 40 million collisions per second, and we do this for an entire year, we'll probably make only a few thousand Higgs bosons that we can actually collect, their decay products. That's very, very rare. And so the other things that we're looking for are things like dark matter or dark forces, right? These have to be very rare, because every single one of you listening to this, every single one of you has about 1 billion particles of dark matter flowing through your body every second. And you've never felt it. It's never interacting with you. It means that your body does not interact with dark matter very much, if at all. So that means that the force by which dark matter interacts with our bodies is something that's very, very weak and very, very rare. Thus, if we might want to have hope of discovering this new thing in our data, we would have to run the collider not just for a year, not just for 10 years, but maybe 20 years. And that's possibly only where the new, the little rare thing could start showing up in our data. Maybe again, we don't choose this, we only measure it. Nature, maybe it only wants to make one of these dark force carriers like once every 5 years. And so if we run, that's fairly Baroque, but once in a very, very rare number of them, and only after 20 years could we start seeing a high enough number of these in right around the same place to let us conclude that we've seen something new. So in that sense, what we have is in terms of, we call it luminosity. We need to run the thing for a very long time, build up a huge amount of data to start hopefully seeing evidence of this new particle. But again, the other part is still totally always there.
we will only have one maximum energy at this Large Hadron Collider ever. Okay, there's some ideas that maybe if you use the same tunnel and you put very, very much stronger magnets, then you could allow these much stronger magnets to allow particles to get to higher accelerations inside the same ring.
I have another idea.
What, please?
Another tunnel on top of that tunnel.
Well.
So instead of going width, you go higher.
Yes. That in fact is more trouble than it's worth, and it doesn't allow you to. Okay. Because if you had you might imagine like stacking a bunch of rings on top of it.
Yeah, I was thinking of that.
Yeah. So, but what that means is that when you do that, each one of those, they don't add up like that, unfortunately. Okay. So you have this kind of, you want to have in this perfect circle all the time, and you can't just add another one on top of each other. Unfortunately, it would be great if we could, because it doesn't really give you what you want to. At the end of the day, you really have to have, because the particles are going very, very fast, right? You need to get them up to, you need to allow them some. You need to basically get to a bigger ring. There's really no way around that at the moment. So that's why the plan now is to build the something called the Future Circular Collider, which is the proposed thing that will be about 100 kilometers around. Wow! Because that's always going to be there, unless we can get to bigger machines and bigger energy, higher energy particle collisions. If nature has particles with high mass m, we'll just never be able to discover them and measure the properties. That's really the only way it is.
And like the Higgs, are we targeting something now, or is something expected to show up, or are we looking and then we say that depends on the amount of particles that we find, or is it something specific that we're looking for?
No, at this point we're at a really interesting juncture in the history of humankind, and I'm not trying to be dramatic, it's just totally true, because the 20th century was such a fast set of developments in physics, as you know, right? I mean, back in the late 1800s, right, once electromagnetism and Maxwell's equations, then suddenly 1905 with relativity, 1915 special relativity, 1930s development of quantum mechanics, later put these things together and get quantum field theory and the Standard Model. This is so like a very rapid set of like almost like clockwork discoveries, and the reason why the 20th century was so unique and rarefied and very kind of privileged is that it was, if you look back on it, it was almost as though everything was progressing in more or less these kind of guaranteed discoveries, right? If you go back at the early parts of the 20th century, it's like it's like, if the equations are correct, there has to be an antiparticle for every particle.
And everything was just happening. It was a continuous sequence of discoveries.
Yeah. And again, that was fantastic. I'm sure that was fantastic for people that were around at the time. But that leads to the point that, and as you know, every time you make a new discovery, it typically raises a bunch more questions than it answers. And that's good. That's really, science, it will continue to progress like, ad infinitum. Again, science is not a list of facts and then we found the last fact, then science is done. Science is a process. Science is a way of thinking about the world. It's a way of asking and answering questions. And so this will always go on. And so over the 20th century, there were all these kind of more or less guaranteed discoveries to be made, and the last one in particle physics was this Higgs boson. That was the last guaranteed discovery. However, now that one's been discovered, there are no more guarantees. There's just a bunch of big open questions and no gigantic sort of huge theoretical flashlights or like, hints in a way, right? It's like, if you're in the dark and then the theorist says, oh, look, my flashlight says right over there should be a discovery, right? We don't have those anymore. We just have big open questions because all of the big ideas that we, the sort of the concrete suggestions of things that we have are basically just ideas that could exist. There's no guarantee for them to be there. For example, there could be, we don't really know why, for example, the neutrinos, these tiny particles that have almost zero mass but not zero. We don't know why they have the masses that they do. Right. One of the ways that we could explain that would be an extension to the Standard Model of particle physics, which would put in some of these things called sterile neutrinos or heavy neutrinos. And these would be kind of partners to these other neutrinos. And maybe we could find those. So that would be
are neutrinos also one of the reasons for the sun, the continuous burning of the sun and energy from the sun?
Yeah. So neutrinos, in fact, are always coming out of the sun all the time.
Okay.
Yeah. So neutrinos are a product anytime you have some kind of nuclear decay.
Okay.
You'll get some kind of neutrino out of it. And so, as you know, the nuclear process, right? So the sun, as you know, is a gigantic nuclear furnace, as we know from the They Might Be Giants song, right? But it's constantly producing this light and heat, and it's also constantly producing from these nuclear interactions going inside. Okay. It's also constantly producing neutrinos. And if you thought it was bad that I said that you have about 1 billion particles of dark matter flowing through your body every second,
you're setting some more down, maybe.
There's in fact way more neutrinos. These are just standard model particles. There's way more neutrinos going through your body. If you hold up your thumb to the sun, there are about, I think it's 10 trillion neutrinos coming from the sun just going through your thumb every second. So there's a lot of these particles all the time. And again, they're super weird. We could have an entire episode about neutrinos themselves. They're very strange because why are they so light? They're not zero mass, so they're not like photons going at light speed, but they're almost there. But they have a non-zero mass. We don't know why this is, and we don't have the big guaranteed discovery. It's possible that there's other very heavy neutrinos that, because they're so heavy, there's this mechanism inside the complicated math that makes it so that the heavy one, it's often referred to as a seesaw mechanism. So you go to the playground, a kid that has more mass is sitting on one side, and the kid that's light, goes up to the very the top of the seesaw, right? So there could be this extra heavy particle neutrinos that exist out there, but there's no reason for them to be there. There's no reason why they have to be there.
They don't interact with the Higgs field, is it, for that to happen?
That's an open question. We don't actually know how neutrinos get their masses. It's possible that they get it through the Higgs field, but possibly not, too. Because the Higgs field is not the only way that individual particles get masses. For example, the W and the Z bosons, those are particles that have masses. They have quite high masses, but they get their masses deliberately through something called the Higgs mechanism. I don't know how much detail we want to go into that, but there's this thing called the Higgs mechanism that is more. It's a complicated process within quantum field theory itself that leads. It's this thing called spontaneous symmetry breaking that allows the particular way that this symmetry is broken in a particular way. It leads to these W and Z bosons having masses, and so we know that there are ways to get masses that are not strictly through interactions with the Higgs field. So yeah, there's this thing called the Higgs mechanism, which is in fact it does lead to the Higgs field itself having this particular value, which means that the other particles interact with this field and they get their masses that way. But for some of the particles, like these W and Z bosons, those get the masses directly from this other thing called the Higgs mechanism itself. And maybe it's too complicated to go into right now. I'm happy to come back at some point and talk more about the Higgs because the math behind it is really fascinating. But again, so in neutrinos, it's suspected that maybe they get their masses that way, but also not. And so that's an open question. We don't really know what the source of neutrino masses is. It doesn't. For example, in the standard model, they don't have to have masses, so they don't necessarily have to get their masses from the Higgs field. So we don't really know where they're getting these masses from, and so it could be some other thing.
Sorry.
No, we were talking about neutrinos. I forget what we were talking about. Neutrinos.
Yeah. I just wanted to ask you. So when you're talking about what's coming up next, maybe for physics or for theoretical physics or what you do, I think a couple of things could be, or the big ones are going to be dark matter and dark energy. And do you see those two as driving a lot of experiments in the future or observations?
Yeah, they have to drive experiments in the future because they're two of the big unsolved questions at the moment. And it relates to the other thing we were talking about, right? Where you asked, are there any big, are we looking for one specific thing with these bigger, the next generation of collider experiment? And the answer is no. And also, but the more profound answer is we don't need to. In fact, we should not be looking for one particular thing. And again, it comes from the fact that as an experimentalist, we are looking for anomalies. We are looking for deviations from what we expect in the absence of a discovery, or deviations from our background noise, if that makes sense, right? So really, my job as a particle physicist, as a collider experimentalist, my job is not to discover new particles. So in the sense that if the Higgs boson discovery was great, and we're very happy to have made it, it almost did a disservice because it makes people think, non-specialists, makes them think that our job is to churn out discoveries by clockwork. That's not what we are. My job is, in fact, to rule out all the possible places in our data or in our phase space, in the physical world itself, rule out places where a discovery could be hiding. And in that sense, what we are is more like map makers. We're like cartographers, right? We have this new uncharted territory. If you go to a higher energy machine and you build a huge amount of data, you have this gigantic data set, you have this uncharted territory, and you just have to map it out. So you have to look in this part. Did you see a discovery there? No. How about this part here? No. And so then you get a chance to rule it out. And so if you miss any of those parts, that means you're being a bad physicist. And if you don't look where you possibly could, it also means that you're being a bad, curious human. So the reason why we have to go to bigger machines is that we have big open questions, of physics right now, and there's no guaranteed answers as to where the answer would be. But if we don't look at higher energies, if we don't look at higher masses, we'll never know what's there. Period.
And also,
that's the answer right there.
Yeah, and also I think you said that we were looking for the Higgs and we found it, but now that it is open-ended, the possibility of finding a particle could actually be a bigger game changer, because if you know what's there and you already are planning and predicting for it till you find it, it's pretty much in line with what your research tells you. But the next particle could actually change reality for us.
Correct. Yeah. Any discoveries we make now beyond the standard model, because the standard model is complete, right? The Higgs boson was the last piece to be plugged into the puzzle of the standard model. But we know that the standard model is incomplete. It's not the full description of nature. So, for example, it doesn't contain gravity. We know that gravity exists, and we know that gravity has nothing to do with the standard model. So, also dark matter. As you pointed out, dark matter. There's no notion of dark matter in the standard model. So we look for extensions to the standard model, and these are things beyond the standard model. And so any discovery we make beyond the standard model will be a total and complete game changer. So that's why it's so important for us as experimentalists to really do our jobs, which is to, of course, we're always interested in the theoretical ideas, but in the theoretical models, but we can't be tied to one particular theoretical model. Our job is not to, the purpose of experimental particle physics is not to determine whether theorists are guessing correctly. It's our job is to do experiments to push as far as we can in terms of parameters and energy and in data collection, and then rule out all the possible places where an anomaly could be found. Once we find the anomaly, then it will be up to the entire community to determine what it is, to interpret it, to put it into our existing framework, and hopefully help explain some of these big open questions. But that's not really why we do what we do. We do these experiments, we go to higher energies, simply because if we don't look at higher energies, we'll never know what's there.
Right. And James, to all my young listeners and university students who have been listening, and I'm surely you've kept them engrossed. I'm engrossed. What would you have as advice for them? So if you had to talk about some of them who want to get into this field, what is your advice going to be? Oh
yeah. So this field, honestly, this field, most people don't choose this field. This field chooses you. Well, so particle physics is the place, again, particle physics chooses you as a person. It's the place you find yourself if you're just simply not satisfied with the other explanations for reality around you, right? Again, this is absolutely nothing against the other sciences. I love the other sciences. If I had a seventh lifetime, I would study biology full time, or I would study information theory, or I would study, flatworms, or I would study. Seriously, I love all these things. I wish I had an infinite number of Jameses to study all of these things.
Maybe they are doing that in other universities.
It's entirely possible, yes. But, particle physics is the place you find yourself where you simply can't help yourself. You've got to know more about this. You want to know what the most fundamental possible rules of the universe really are. And in that sense, it's sort of like it chooses you out of all the other possible things that you could work on. And so in that sense, intellectually, that's what happens, right? It's sort of like intellectually and emotionally, it's like, you're drawn to this just because it's like, wow, look at this. The fact that we as humans can really come up with mathematical models and experiments that test those mathematical models at such precise levels, that is absolutely mind-blowing and astounding and gobsmacking, and that's why so many of us, thousands of us, come to this place, because nothing else was satisfying to us. We had to go to the very extreme limits of human knowledge. And if you're that sort of person, you'll know it, and you'll definitely get into particle physics. In a practical sense, the way you do it is you recognize how important math is. You recognize that mathematics is the language of the universe. It really is. So, for example, if we were able to ever come into contact with another, set of beings somewhere in the universe, and they had an intelligence that was similar to ours, we're not going to talk to them with English. We're not going to talk to them with Farsi. We're not going to talk to them with, anything. We're going to somehow talk to them via math. We're going to realize that we have independently discovered the mathematical rules by which the universe operates. Maybe we have different symbols or different ways of putting them down, but we'll realize that those equivalents are there, and that's how we're going to be able to communicate with them. So math, as you know, is absolutely important. Because we do live in a mathematical universe. That's something that'd be fun to have an entire episode about, is to talk about the mathematical universe. Why is it that our universe seems to choose a few different mathematical objects to actualize very, very precisely, but mathematicians can conceptualize a large number of possible mathematical objects that our universe seems to have no use for? Why is that? Anyway, so in the practical sense, math is obviously important, and making sure that you have really good resources available, textbooks and like classes and things like that. But at the end of the day, also what the particle physicist is again, it goes back to the thing we talked about at the very beginning. Particle physicist is the person who never accepts that's just the way it is as an answer. They never accept, there's no answer for the thing that I'm looking for, the question I'm asking right now. I can't find the answer in the things that are around me right now, so I guess I'll just give up. That's the opposite of the way the particle physicist thinks. The particle physicist looks at a barrier to understanding something, and they don't say, well, I guess I'll give up. They say, how could I possibly answer this question? And if the tools don't exist around you to answer the question, you go and find them. And if they don't exist anywhere, you create them. So that's really the way the particle physicist operates in the world. They recognize that the physical world has rules, it has these kind of structures around it, and it doesn't matter that whether we think that they're elegant or they're beautiful or they're convenient or they're simple. Simplicity is not a scientific concept. If you have some kind of, if you have a problem, if you have some kind of observation in front of you that doesn't make any sense given our current understanding of nature, you go in search of the answer, and sometimes that requires you to invent totally new methods and think completely outside of every box that's ever existed. In fact, inventing an entirely new box, that's what a particle physicist is. And if you're that sort of person, you'll know it. And if you want to become that sort of person, then start thinking that way. Start thinking outside of all the parameters that are given you. For example, if your teacher says, okay, no, you have 20 homework questions, and you have to answer the exact precise answers from this book right now. But the book is it doesn't do a very good description of the problem, or or the book is vague in certain places. Don't just say, well, I couldn't answer it because the book was bad. Find another book. Look at the concept itself. Think about what is being said in the question itself. And if you do that, that will allow you to start to think the way that a physicist does. Start to think in the way that a particle physicist thinks about the nature of nature and the universe itself, the way everything works. And that's the way that a particle physicist is evolved, is born, is constructed.
That's so inspiring, James. That's really inspiring. I think we can use a lot of what you've said at work as well, because the principles that you've just highlighted have really been, can be exercised in other fields as well. James, do you have any favorite books that you would like to recommend, or you want? Do you have any? What's your favorite book?
When research gets very, very busy, I don't get a chance to read a lot, but it starts to go down. But then, of course, I'm one of these people that's always been reading multiple books my entire life, right? Yeah. So right now, for example, I don't know. Right now, I'm reading the novel G by John Berger from the 1960s. He won the Booker Prize for that. Mm-hmm. I'm also reading a book called Kids These Days, which is about about the millennial generation, and about how economic and social trends have created a situation where the contemporary millennial generation has more or less been deprived of opportunities that existed in the past. I'm looking forward to a couple of other books right now. I recently read a fantastic book by a journalist named Angela Saini, and it's called Superior. I highly recommend that to everyone. In fact, that's my biggest recommendation right now. It's called Superior by Angela Saini, and she talks about the very troubling rise of non-scientific, pseudoscientific, quote-unquote race science, and about how so many people around the world are trying to use discredited ideas, pseudoscientific ideas, to justify bigotry and hatred. That's a fantastic book. In terms of science books, of course, I would not be where I am right now. I would not be a particle physicist if it weren't for the book The Elegant Universe by Brian Greene.
Oh yeah, that's my favorite.
And I assume.
Well.
I hope everybody has read that multiple times. And if you've never read it, you should absolutely read it.
Big fan of Brian Greene.
Yeah, no, Brian's great. So that in terms of fundamental books for me, that's in terms of science ones, that's one of the most formative ones for me. But I read a lot of poetry, I read a lot of biography, I read a lot of everything. And the other thing that I would highly recommend is that everybody wait for about 1 year from now when my book will be out, maybe 2 books. So look forward to that.
If we want to get to know a little bit more about you, would you want to tell us about either your website or where could they connect with you online? Please tell us about your book as well.
Yeah, so I'm easily searchable online. So like I mentioned, I'm a full-time researcher here, and that's my day job and that's my passion. But I'm also very passionate about making sure that people recognize that my research is actually your research. As I hope that people have understood through this, as I hope people have understood through this conversation, when you get these really complex concepts, you break them down into their pieces, you find a little kernel, you realize that it's really just coming from a very simple, almost childlike curiosity place, right? All the research that we do here is really just trying to answer some very basic questions that everyone has asked themselves at some point. Really, it's like, where did we come from? How does everything work around us? And where are we going? Those are the questions. It's just the answers get very complex, and the ways that we do it gets a little bit labyrinthine. But that's really where the research comes from, in the sort of fire in the belly and in the heart. This desire to know more about the universe. And so, my kind of hobby is sort of taken on a life of its own over the last few years as I've become more and more well known as a public-facing scientist. So I do a lot of public speaking around the world, and so in fact, once I spoke, the closest I've gotten to I spoke in Mumbai, for example, once, and I speak all over the world, though, in a lot of venues. I do not have a YouTube channel. People keep telling me that I should start a YouTube channel, but again, if I had a 7th version of myself, I definitely would have started a YouTube channel already. But you can find me. I'm easily searchable online. You can also go to jbbeacham.com, and that has a list of all of my public appearances and some of my other projects that I'm working on and my research and things like that. I don't use social media very much except for Twitter, so feel free to follow me on Twitter. That would be fantastic. And mostly because then once I get closer to when my book is coming out, that would be an easy way to find out more about it. In terms of the book that I'm interested, the one that I'm putting together right now, there's several different books that I want to write. The first one that I think I'm going to focus on is the fact that underlines so much of what we have been talking about here. This kind of like this, in fact, goes back to the original quote that you were talking about, right? From a politician is saying, if you can explain what you're doing in terms of the politician would understand, then you can have money for your project. My book is interested in exploring the concept that the entire basis of that discussion is in fact kind of bad, right? Why should basic science, why should scientific ideas that are just about understanding nature itself, understanding the basic rules of the universe because we're curious, why should those be subject to the funding whims of politicians? So it would be a book about how the current system, so many of the current socioeconomic systems that we have right now, they in fact stifle science. They impede scientific progress. When you have an entire society that's based primarily upon profit, people making profit for things, that changes everybody's mindset so that the only scientific projects that are pursued are primarily the ones that will eventually create profit for individuals. So even it happens in my field, right? I mean, most of the research that we do here, you're never going to make a product out of the Higgs boson, but because this type of research historically has been attached to, things like energy sources or, military or defense, nothing that we do here can ever have a military purpose. By design, it will never be possible to make, what we do into a bomb. But also, it's not really going to give us energy sources. It's really just because we're curious about nature. But when you have a society where the basic, the highest goal is possibly to create profit for people, it makes it so that only certain types of projects are pursued. And that does a disservice to everybody, and not just in kind of intellectual senses, because our ability to explore the universe is stifled, but also in practical sense, because, for example, pharmaceuticals, right? I mean, only certain types of drugs are pursued to be developed in pharmaceutical trials. Those ones that will create profit for the companies themselves. But there's so many other things that if we were able to just give lots and lots of resources to curious scientists that want to either solve problems that are intellectual or practical, we would have much, much better, society. For example, why do we have an antibiotic shortage right now? This should be that's insane for an advanced society in the year 2020 to have an antibiotic shortage. But instead, we have pharmaceutical companies that are extremely interested in, creating designer drugs for people that have a lot of money to pay for, like lifestyle drugs, right? This is completely backwards. Anyway, so the book will be about that, about how, can we really dare ourselves to think big, and not just think big in terms of the next particle physics experiment or, something new with respect to CRISPR or new deep learning techniques to do da-da-da, but really thinking big in the sense that what if we were able to achieve a global society where we did not have just the profit motive behind the scenes, constricting funding toward big science, constricting funding, and resources to scientists, who really just want to push the boundaries of human knowledge. And in fact, that would help everything. It would help science. It would help technology, because, the smartphone, for example, that you have in your pocket, maybe it seems like it was a great invention, but it's really just a small computer. This is not such a quantum leap forward, if you want to use the language we were using earlier. Right? Yeah. It's really just an incremental change. It's a marketing change. The things that we think of and valorize as big steps forward are not really big at all. And I want to create I want us to allow ourselves in the 21st century to have a knowledge revolution, to really think bigger beyond what we have now, and maybe start positing that we can organize things so that we don't have just the profit motive behind the scenes that supports all of the science and the technology and the innovation that we do. So that will, that of course relates to, it affects particle physics, big experiments like the Future Circular Collider, because, why should we stop at a Future Circular Collider? Why is 100 kilometers enough? The answer is it's not. We should go bigger. We should build something, around the circumference of the moon or around the outer edge of the solar system or something like that, right? Yeah. And why should we stop just at at particular types of sequencing a genome, just so we can understand about a particular disease or something like? Why should we not go bigger than that? What would genomicists do if they had more or less unlimited resources? What if we were able to set up things so that we didn't put so much money and so many of our resources toward knowingly wasteful programs like, for example, $1 trillion fighter jet in the United States that's never been used, that will never be used. These are resources that are being chosen to be used in a particular way by people that only really have their own interest at heart. So anyway, it's more like it's going to be a 21st century manifesto for a revolution in knowledge and a revolution in science and technology and innovation for everybody, so that we can create a better world for everybody around us. So that's the first book that I'm kind of working on.
That's beautiful. That echoes a lot of what we are trying to do here in our own small way at Indian Genes as well. So yes, we are looking forward to the scientific revolution, the spread of knowledge to everybody, especially people who are listening to us and kids around here. So I think that's a great meeting of minds here.
Yes, I think what you're doing is fantastic, and I totally support it. It's one of the reasons why I was very happy to get your invitation.
And before we end, James, I once again want to thank you for all the time that you've spent talking to us. It's been so engaging. We've enjoyed talking to you. I've spent the last, I don't know, I've not looked at the watch. In fact, after the first 1 hour, I've switched off the watch and I just closed my eyes and I was listening to you and talking. So I just wanted to get into the conversation. So I just hope that you've enjoyed your time with us, James, and you're welcome back anytime. Anytime you just call us and we can talk again.
Oh, it was my pleasure. Thank you so much for having me, and I think that what you're doing is a fantastic thing, and I think that I can tell that we have very similar philosophical attitudes toward toward knowledge and physics and inquiry itself. So yeah, I'd be more than happy to come back if anyone's interested at some point in the future.
Thank you so much, James. Thanks a lot.
Thank you so much for having me.